So let's move on with the tutorial now. And so as usual, when I start these, I try to go through the logic first for why we are solving these problems and how they fit into the context of the course in general. So in the first couple of tutorials, we looked at taking your real world problem and developing the model for that. Then we translated the model. So we translated the ordinary differential equations into the deviation form, and that helped us eliminate some constants. And in that way, we were able to convert the model into a transfer function. So we are able to Laplace transform into the S domain. And once we are in the S domain, we have access to these analysis methods. So we saw last time that with our root locus plotting, we could look for the roots of this equation. So remember, the denominator of the closed loop function was 1 plus the open loop transfer function. So when the denominator went to 0, then we were finding the poles, and it turned out that the places where that went to 0 were the time constants of the solution. So we are solving this also because we are trying to avoid a root having a positive real part. So we know if we get a positive real part for a root, then we have the onset of instability. So that partly motivates what we are doing now. So we know that the roots are going to reside where the open loop function equals -1, right? So from this, we can see that when we are close to -1, then we are starting to detect for a possible instability. And we are going to look at this more rigorously in the materials. So if you've covered notes 6, you will follow the exact logic for closeness to -1, 0 being instability. So the closer our open loop function goes to -1, 0, the closer we are to instability. So that's if we apply S equals I omega, right? And you'll notice in the notes also, the basic theorem gives us that if we take the magnitude of S equals I omega in our transfer function, then we get the magnitude ratio, and then the argument of the same function, that's the phase angle. So remember, when we looked at the linear responses, we said that the magnitude ratio was how far the system jumped. So if you apply a sine wave on the input, the system, so if you are applying a fixed sine wave, then the system will jump initially in response to that sine wave, and then it will steady out to its own sine wave. So we are concerned about that first jump. So the magnitude ratio relates to how far that first jump is going to be, and the phase angle relates to how long it's going to take before it gives us that complete first jump. So those metrics give us some idea about the so-called frequency response of the system. Right, frequency response, because we are applying a sine wave or some oscillating function, we are applying some wave. So that wave is going to have some frequency. So how does the system respond to this frequency? So the basic theorem, which is derived in detail and proved in detail in the notes, it tells us that if we just apply I omega in our function and take the magnitude of that, then that is going to give us the magnitude of the jump, and the argument of that same function will tell us how long it takes. Right, so that's the basic theorem. And if we investigate this function, then we can think about how close that comes to -1, 0. So like I say, the complete logic that outlines exactly why that works and how important that is, that's in note 6, and we do need another session to go through just those notes and answer any questions, because it's really the basis of the whole course, right? Up to now, it's been deriving your model and translating it to the Laplace domain. That's all fairly mechanical. There's a fixed way to do those things, right? The guts of the course reside in understanding why this works. So we will get to that. For today, however, we are going to just first try to understand how we can visualize these things. So generally accepting that this closeness is important, we are just going to look at how can we visualize this? How can we take a complicated function and understand how close it comes to -1, 0? And we have these three types of plots to help us do that. So Boddy, Nyquist, and Nichols, these are three different ways of visualizing the same information. So our function g of I omega, of course, it has a real part and an imaginary part, then it has a magnitude. So if you convert that into polar coordinates, then you can talk about a magnitude and an angle. We are going to use those concepts and plot out our function in different ways. And you'll see we have some nice ways of looking at how close we get to this -1, 0 point. Right, so as I say, you've got notes 06 to look at the logic for why that matters. You also have the YouTube video. So in the YouTube video, we do that quite rigorously, but we'll also have another Zoom session just on that topic. Any questions or comments so far? Okay, if not, you may have noticed that I've put out a bit of code, as I often do, and that's we won't get into how the code works and so on, but it's going to help us plot out the functions of interest very quickly here. So it's just a method for us to be able to visualize what we have. And so I'm just going to load all these functions into memory. And here's the first plot. So the Nyquist plot is simply a plot of the imaginary part against the real part. So we have some transfer function. And in fact, let's first develop that a bit. So let's say we have this transfer function. So G is 1 over S plus 1. And then we want to apply S equals I omega. So if we write this as G of I omega, then that's 1 over I omega plus 1. Right, and we don't like a complex number in the denominator here, so let's multiply numerator and denominator by 1 minus I omega. And in fact, let's rewrite this slightly differently. So let's write it as 1 plus I omega. So multiplying here. Right, and if you look at the denominator, it's the product of complementary functions. So your factor here has a plus and a minus. So it's basically it's essentially this factor squared minus this factor squared. So it's going to be 1 squared minus I squared omega squared. So I squared is, of course, minus 1. So this works out to, so keeping the numerator as it is. And then in the denominator, we are going to have 1 squared, which is 1. And then we have omega squared, we have minus omega squared I squared. And I squared, of course, is minus 1. So this works out to 1 plus omega squared. Right, so that's G of I omega. Now the denominator is a real number only, and then only the numerator is a complex number. And so we can see here the real part is 1 over 1 plus omega squared, and the imaginary part is omega over 1 plus omega squared. So as we vary omega, we are going to create a series of real and imaginary numbers. So you can see in terms of the real part, as omega varies from 0 off to infinity, we can see the real part is going to start at a 1. And then as omega goes to infinity, the real part becomes 0. And then for the imaginary part, when omega is 0, it starts from 0. And as we go off to infinity, the omega squared down here is going to beat the omega up here. So this is going to go off to 0 as well. So the imaginary part starts on 0, and the real part starts on 1. And you can imagine plotting that out, but it's done for us here. And I'm just going to take one of these off. So in this code, if you want to visualize any function, you just create the function here. So I've created a function f1, which is giving us back 1 over s plus 1. So that's the function of interest. And so we just say gen frequency domain dynamics plots. We specify GP equals f1, so the function we created, we just specify that there. And we can provide a range of omega values. So a log space means we are starting at a very small value of omega, and we are going up to a value of 100 and using 1,000,000 data points. So if we run that, right, you get the Nyquist plot. And by the way, if you read in the code, you'll see the starting point is marked with a blue X, and the end point is marked with a red dot. We are also marking the point -1, 0, right? We said real part -1 and imaginary part 0. That's a kind of critical point for us. And we can see our function is not going anywhere near there. But let's just understand the function first. We said when omega is 0, right? When omega is 0, the real part here is going to be 1 over 1 plus 0, so that's a 1. So we can see here the real part, right? Here's the real part. It's on a value of 1, right? And the imaginary part, we said omega over 1 plus omega squared. When omega is 0, then that's 0 over 1, which is 0. So the imaginary part is a 0. So we are starting out here, and then we can see we seem to be increasing in this way. And if we think about what's happening here, if you start increasing omega past the 0, and let's say it's a small increase in omega, then your real part will stay approximately 1, right? For a small omega, the real part is still approximately 1. And for omega, we are decreasing the value from 0. So our imaginary part is becoming more negative here. And you can see that happening, right? Our function is starting to move in this direction. So the real part is staying close to 1, and the imaginary part is becoming more negative. So we are starting to move down like this. And then coming back here, we can see that as omega goes to infinity, the denominator starts dominating the whole term, and this whole thing starts to go to 0 for both the real and imaginary parts. So you can see, you can imagine that the process is being pulled in terms of the real number, it's being pulled in this direction, and in terms of the imaginary part, it's also being pulled in this direction. So we start here and we get pulled in towards the 0. Right? Any questions or comments on that? Okay, so that's what we can do in terms of just simply plotting out the real and imaginary parts for g of I omega. Now, this that's all well and good for a nice, easy function like this one. But let's say we start increasing the level of difficulty. Let's say we put some arbitrarily complicated function in here. And just randomly, I'm using some numbers. And in Python, the double multiplication or the double asterisk gives you raised to the power. So let's see what that looks like. And I think I've got an extra bracket here. Okay, well, yeah, so there's something going on that we don't expect. And it's perhaps not so easy for us to figure out what the asymptotes are and how this function is going to behave over time. So we want a way to investigate this plane more rigorously. And in fact, if you look at what we have here, this looks like a very simple transfer function. But there are some other views where certain features that were not really visible here, there are certain features. You can see here we are plotting against omega. So looking at the behavior of this function as a function of the frequency, we start to see certain features that weren't visible otherwise. So the Nyquist plot by itself gives you a certain amount of information, but let's now think about more complicated functions and what we can do to improve our visualization there. So that's what we're saying here. We are introducing now this definition of L, the log modulus, and its definition is this. So it's the number 20 multiplied by log 10 of the magnitude. So of course, if we have the real and imaginary parts of G, then we can easily calculate the magnitude in the usual way. So the real part of G squared plus the imaginary parts. So we can easily get the magnitude of G in this way. And according to the log modulus, all we then have to do is take the log to the base n and multiply that by 20. So there's no sort of hidden operation here. This is a straightforward take the magnitude and process it in this particular way. And the advantage of using a log in this definition for L is that we can start to break down our function G. So of course we can, if we are able to write G as the product of two functions, let's say G could be written as the product F1 and F2, then of course we can take advantage of this property of the logarithm and rewrite this as 20 log 10 of F1 plus 20 log 10 F2, right? So that we'll see has an advantage in terms of plotting out the function and finding the behavior. Let's say on the other hand that this was F1 divided by F2. Right, then we could recognize that F2 could be F2, well, this function could be rewritten as F1 times 1 over F2. And the log of 1 over something can be rewritten as just minus that something. So we can see that if we have some complicated ratio of polynomials, then number one, we could separate those two sets of polynomials as a numerator and denominator and just look at the difference between those two. And number two, we can always take a polynomial and factorize it into a set of terms. And so we can break down a polynomial like that. So let's say F1 had multiple factors. Let's say F1 could be rewritten as well, let's do it here. So let's say F1 could be rewritten as S plus K1 S plus K2 and so on. And similarly for F2, let's say that could be written as a polynomial in that way as well. Then you see all that happens is we get more terms down here. So we would simply have the magnitude of S plus K1 and then S plus K2 and then minus magnitude of S plus M1 and minus S plus M2 and so on. Right, so if you have some function which is quite complicated, here's the reminder, by the way, just restart the session if you get disconnected. So if you have some complicated function, we know that we can always convert a function into a polynomial using a Taylor's series. And so we can then translate any complicated function into the sum of simple logarithm terms, and where we are linear in S. And that's quite useful because if we can find a term like that, if we have a way to write it as 20 log 10 S plus K, and we know that we are looking at S equals I omega, then we can think about what that individual function is going to look like. So as omega goes to infinity, you can see that this term is going to be much larger than this one. So we can say this is negligibly small and ignore that. And so this thing becomes approximately 20 log 10 I omega. So we have one easy asymptote. And then, of course, we can also say at omega equals 0, then this term is simply 20 log 10 K. So if we have the value K, we can just we can just get a constant. And that's plotted here. So let's go back to our original function. And now we've gone and worked out L and theta. Well, we worked out L. And you can see here, our K in effect is going to be 1. Right, so where we were saying I omega plus K, so it's S plus K, in our case K equals 1. So it's the log of 1. So log of 1 is of course a 0. So for low values of omega, we are at 0. And then as omega passes a certain value, right, when omega becomes large enough, then I omega dominates K. And so this term becomes approximately 20 log 10 I omega. Now we are plotting this on a log of omega scale here. So although it says omega here, well, it is omega, but this is a log scale, right? So you can see logarithmically scaled numbers. And so plotting against the log of omega, you can see that it's going to be a constant gradient, right? So that means we just need two numbers. So we've got a single number here, the intercept. So that's that line. And then we know that if it's linear in S, then it's going to be a straight line down like that. then the question is, where do I put this straight line, right? Where should I start drawing this, this asymptote down like that? And if you look up with this kind of asymptote, you can show that at the value of omega is 1 over tau. That's where this line is going to intersect with that straight line there. So it's as easy as that. We just need to look for 1 over tau, and tau being, of course, the time constant there. So remember the standard, in the standard form, we write tau s plus 1. So if g equals tau s plus 1, that's the value of tau that you have there is going to be the number you stick in here, and that gives you the value where we are switching from the flat line to the 20 decibel line. So we call it the 20 decibel line because you can see the gradient is going to be 20, and then we can see that's on the basis of log 10 scaling. So that's the so-called 20 decibel line. Okay, so we can see now that we can take any complex function in G, translate it into a set of functions in S, and we can plot each one of these out on our L graphs. And let's do that here. So let's say we have some complex function. So let's say we are interested in the function s plus 3 over s plus 1. So our numerator, okay, let's leave that, that's our denominator, and then our numerator is s plus 3. And down here, I've got, you see, f1 times f2. So that's just the product of these two. And you can see the product of these two is s plus 3 over s plus 1. And so we are going to plot out all these functions. So f1, f2, and f1, f2. Okay, so
sorry, sir. I have a question about the code, just quickly, if that's okay.
So shall I walk you through the code quickly?
It was just on my computer. I can open it as you've sent it to us on Dropbox, and it will display the graphs for that first function it plotted. But if I'm to comment out that function and uncomment another one, it gives me errors, even though I've run the other blocks. So I'm not sure quite why it does that. It doesn't plot the other ones.
Okay, I know I've changed this function a bit. Let me just make sure you've got the right version of this. See, I have a kind of development side and a production side. So this is the latest version of the Python code. And then this is the distribution folder. So I know I did change the code a bit, and I must have neglected to update this folder. So please try running, please close the folder you've got open, sorry, the file you've got open, and try reloading. Just make sure your Dropbox updates to this time, and then reload that file.
Okay.
And it should load. Okay.
Okay, thank you.
Thanks. Okay. So here we are looking at the product of these two, and the blue line is going to be the first one. This looks quite different to what we saw last time. Remember last time we saw it started at 1, 0, and then it looped its way in towards 0. And you can't see much of that loop here, and that's just because of the scale now, right? Because now we have an s plus 3, that one is actually rushing off to infinity here. So it's moved the scale of our imaginary axis quite a bit. You can see here the real axis is -1 to 3, whereas this is going to from 0 to 100. And in fact, if we just take this off, if we uncomment this, well, I'm not going to do it because it seems to take a while to run, but you'll find again that curve. So you can see a slight curve here, but you can see it better if you comment these lines out. So that was the curve we saw before, starting at 0 and looping in towards, starting at 1 and looping into the 0. And then we've got this, this new line here, and this is the second function. And you can verify this with a small derivation. So we've got g equals s plus 3. And of course, for s, we are applying now I omega. And so clearly, our real part is always going to be a 3, right? It's not like this case where we had to take the complementary complex number and multiply it. This is in the numerator, so we are looking directly at the function. And we can see here the real part is always going to be a 3, and the imaginary part is in direct proportion to omega. So there's no denominator with omega squared this time. So the real part, you can see that here. So the real part is on 3, and remember we said I used a blue cross for the start of the function. So you can see the imaginary part is on a 0 here. And as omega increases, and remember we are applying, this is log space 2, so that means 100. So we are going from 10 to the minus 5 to 100. So omega goes up to 100, and we can see 100 here. So this is the second contribution, right? And you can see here, those are the two functions. So 1 over s plus 1 and s plus 3 give us these two lines, this one and this one. And of course, from this plot, we can't see an easy way to make the combination of the two. So of course, I've gone and generated the product of these two functions. And that's how we plot this, right? We use all this code and it goes and plots this for us. But there isn't an easy graphical way that we can imagine combining these two functions together and getting this function, right? So the Nyquist plot does help us understand how the complex numbers are shifting around in the space. But in terms of combining functions and multiplying functions, there isn't an easy way we can think of to do that, right? Not on this plot. But now we have this, this L function. And here's the first one. So we know 1 over s plus 1 looks like this. And then we've got s plus 3 as well. So here's s plus 3. And now we can easily imagine a way to estimate the overall or the contribution of these two. Because we know in the L domain, we can simply add together these two functions. So once more, s plus 3 is this orange line, which is hidden by the green one here. So the green one is actually the combination of the two. And actually, okay, it's fine. Let's just keep it like that. So there's we basically have to add together these two values. So we are adding 0 to probably 10 here. And so that's not changing anything. So we are getting a 10 as our resulting function. And then when we get down here, of course, this is an s plus 1. So this term starts to make its contribution first. And so our net result is going to be that this, this is going to curve down, right? So it starts to curve down. And all the while, this s plus 3 function is increasing. So it's from around this point, it starts increasing. And when we get to around the 1 over 3, then you can see the contribution from the s plus 3 term is about the same as the contribution from the 1 over s plus 1 term. And this one has a gradient of 20, and this one has a gradient of minus 20. And so those two will cancel each other out and we'll get to a 0. So that's the great advantage of the L version of our G function. we can break down our g function into numerator and denominator, and we can split up each of those polynomials and then just plot them out on this L versus omega graph. And so we can easily figure out what our function actually looks like. So plotting S plus K either as a numerator or a denominator, it just means there's going to be a flat part and there's going to be a part that goes up or goes down. And then that flat part will move up and down depending on the intercept. So here, because we had a 3, right, log 10 of 3, remember log 10 of 10 is about 1. Log 10 of a very small number is going to be closer to 0. So log 10 of 3, maybe that's on the order of a 2 or something like that. And then that times 20, that's going to give us the number that's here. Right, so there's that flat part, and then it's going to curve up, and then the flat part, and that curves down, and then we just add the two together. So on the same set of axes, you just pick some value. So for some fixed omega value, you add together two values, and then you make a mark for your solution. So I'm describing here, of course, how you would answer such a question during an assessment, right? Of course, if you write code, you can just go and add the two vectors of numbers together, which is, of course, how this is done. So, so that's how we can find, we can determine the overall response of the system. And as we said before, when plotting it this way, we tend to expose much better any features that are in this graph. That's to some extent because of the nature of log. When we logarithmically space things out, we tend to exaggerate certain features in certain places to a better degree, and so that's how we can find features better like this. Right, so that's the first part of the Bode plot, right? The log modulus. And this relates just to the magnitude of the resulting complex number. Then, of course, to complete the picture, we also need the angle. So the angle is, of course, going to be log G, and that's always going to be equal to the arctan of the ratio imaginary part of G over the real part of G. Right, so we can see easily how to find the imaginary and the real parts. And for this example, of course, that's going to be arctan of, so the denominators will cancel, and it's just going to be omega over 1 or minus omega over 1. So it's arctan of minus omega. Right. Now, that is true. We can do it this way. We can just work out the arctan of a scalar. But as you know, in the complex plane, you have these quadrants, right? And let's just go over here. So it could be for positive numbers, we could be, let's see, that's the positive side of the plane. So our angles could be calculated around here. But then also if both parts are negative, the angle could end up here. So a better way to avoid that 2 pi error where if you take the arctan of a single number, it doesn't know which plane to put you in. And so your calculator will just go ahead and stick you in the closest one or something like that, which might not be the best for you, especially when trying to plot these graphs. Then quite often in your calculator or in your programming language, you'll have an arctan function which supports an imaginary part and a real part. So make sure you are familiar on your calculator with working out the arctan when given 2 arguments. So you want the 2-argument arctan calculation, because that's going to give you the angle in the right quadrant. Right? And in Python, you'll see that arctan, I think it's arctan2. Yeah, so here you see in Python, in the NumPy library, you have arctan2, and that lets you specify imaginary parts and real parts. And so then you know that you are getting a reasonably shaped theta value. So like before, you can plot out your angle for each of your functions. So here for 1 over s plus 1 and for 3 plus s, we can plot out our angles. And then the sum of those two angles is going to be the overall transfer function. Right, so that's how we generate L and theta. And by the way, here the scale, I've just divided by pi so that it's a bit easier to read. And actually in Bode plots, they normally work in degrees, so not in radians. So here I'm actually showing radians divided by pi, but normally in a Bode plot, you convert that to degrees. So you can get rid of this divide by pi, and then instead multiply, you divide by 2 pi and multiply by 360 to get that in degrees. So that's the Bode plot. And we'll spend a lot of time on Bode plots. Of course, it helps us construct the function easily. And in its own right, it has a nicely defined closeness to 0. So I didn't mention this red line so far. So I put in a red line here and a red line here. And the reason I did that was because I want to point at this value. Remember we said we are concerned about our transfer function leading us to this -1, 0 point. So if you think about this point, it has a magnitude of 1 and an angle of pi or minus pi, right? So here's 0, the origin, and here's the point -1, 0. So we are pointing in this direction, and we have a magnitude of 1 and an angle of pi, right? An angle of pi. So to represent that on our Bode plot, number one, if it's if it has a magnitude of 1, then log 10 of the 1 is going to be a 0, right? And you can multiply by the 20, but it's a 0. So number one, the L is 0 there. Number two, your angle is going to be pi. So here you can see minus pi. So most of my values are negative here. So maybe I should do one for pi and another one for 1. And so just by looking at these two graphs together, you can ask yourself, okay, when am I close to 0? Okay, I start out always being close to 0. But if I look there, when I'm close to 0, I'm never close to minus pi. So I'm not close to minus pi here. So I don't have to worry about omega in this region, right? Number one, even though I'm close to 0, which means my magnitude is close to 1, my angle is not close to pi, and we can see that here. So even though we are close to a magnitude of 1 sometimes on this plane, we are never simultaneously close to a pi. So that means we are not going close to a -1. So that may seem to you to be a very roundabout way of looking at -1, 0. And that's because on the Bode diagram, it gives us all these advantages of being able to add together curves and so on. But the disadvantage is that we can't so easily see where the -1, 0 point is. And so we have to a little bit navigate these two lines, right? So we can see here, yes, we are close to 0 here, but at that time we are not close to plus or minus pi, so that's fine. We do get close to 0 again here, but when we are there, we can see again, we are not close to plus or minus pi. In fact, we are as far away from those values as we could possibly get, right? It's right in between those two values. So neither here nor there is a cause for concern. And then in this region, which is about here, still neither the overall function nor these individual functions are going close to that angle of plus or minus pi. So in our kind of roundabout way, we can see from the Bode diagram that we are not going anywhere close to minus 1, 0. So we don't have to worry about instability for this function, right? So that's how we start to look at Bode diagrams. Now there is yet another way of viewing, another way of visualizing the transfer function, which is the Nichols chart. And at the moment, it's a little bit difficult to justify the Nichols chart. And that's because this chart is very useful quite later on. So later on, when we are actually talking about optimizing our control parameters. So remember, we are doing all this because we are trying to tune some controller. We are trying to fix the constant for the proportional controller, the derivative, and the integral parts of that controller. And the Nichols chart, it turns out, is going to help us tune those parameters very easily. And just as a brief motivation for it, we can see that the critical point, we know, let's say minus pi, so minus 180 degrees is somewhere here, and that's at L equals 0. So I forgot to say, we are plotting L against theta. So the angle is here and the magnitude is there. And so at this point, that's the critical point for us. Now we've gone and plotted our function here, and we can think about how this function is going to move around in relation to that point. So as we, for example, change the proportional constant or the integral constant and so on, this curve, this overall function is going to shift and move around, and it might take us closer to this region. So that's what we are eventually going to use the Nichols chart for. For right now, let's not worry about all this stuff going on here. So we'll explain about these closed loop lines later on. For now, let's just think about how we would plot on the Nichols chart. So the Nichols chart doesn't show us the frequency omega anywhere. And that's because this is a locus of points in L and theta. In other words, if you take the Bode diagram and you select a series of values for omega. So let's say we take omega at 10 to the minus 2. Then we can look up the L value there. Let's say that's 10. And we can look up the theta value there. Let's say that's 0. And so we found a point 0, 10. So we just go over here and 0 and 10, and we plot that point there. Right, so that's how we create the Nichols chart. We select a series of values in omega, and that gives us a series of L's and thetas. And then we just plot each of those points, and that draws out a curve for us. By the way, it didn't plot at 10, 0 because there's this function is being overwritten, and there's a bit of a correction for me to do on the Nichols chart. So don't worry if you don't see a 10, 0 here. So anyway, we can plot out the whole function here, and we'll see this is tremendously useful for doing what we promised to do at the beginning, which is actually go and tune a controller. Okay, any questions or comments there? Okay, if not, let's look at, let's take one of the other examples. So we can see how to do our plots for polynomial type functions. Just to be different, let's take this transfer function e to the, let's say e to the s. E to the s. So let's say that was our transfer function. Then we can break that down into real and imaginary parts if we apply s equals I omega. So that's e to the I omega. And I hope you are all saying, yeah, the Euler formula applies then. So the real part is cos of omega plus I sine of omega. It's a direct application of Euler's formula. The real part is cos of omega and the imaginary part is sine of omega. Just have a look at your Euler's formula and you'll see that's true. Okay, now that's if you want to convert to Cartesian coordinates. If you want to write this in polar coordinates, it's quite easy. You can say that the magnitude of e to the I omega right, that's simply a 1, right? So from your basic complex analysis, the magnitude of e to the I omega is 1, and the angle, so arg e to the I omega that's equal to omega. Right, so we have the magnitude and the angle quite easily there. So you can say that L then is simply going to be 0. So L equals 0. And well, the angle will be omega. So we are doing this now because we want to anticipate what these functions are going to look like, right? We don't want to always rely on brute force tools like computing that's just going to give us the answer. So can we visualize what this would look like first? So we can see that the magnitude is a 1, so and the angle is changing. So we expect it's going to be a circle. So and also just from looking at the cos and the sine there, we can also see a circle. So we expect that on the Nyquist plot, we'll see a circle. And then we can also expect that on our Bode plot, because we've got L equals 0, so L will just be a flat 0. And then our angle, that's just omega. So that one is, in principle, that would be a straight line. But remember, we are plotting on a log basis also. So anyway, let's try it and see. So let's change our functions. Let's just make this F4. So by default, Python won't have an exponential function, so you have to get it through the NumPy library. So anyway, and let's just do this as a new call. F4, we can play around with the frequencies a bit, but let's just see what this gives us. Right, so as we said, we expect to see a circle in Cartesian coordinates. And in fact, it's just because of my spacing, because I've stretched out the x-axis a bit compared with the y-axis, that it doesn't look quite like a circle, but that is a circle. You can see radius of 1 here, radius of 1 here, right? So 0 to 1, 0 to 1. So that's a pure circle. And then here you can see, it looks like we are painting our screen with values that are not 0. But if you look at the scale here, this is 10 to the minus 15. So that's the numerical limit of the computer, right? So when it calculates the cos and the sine and the magnitudes and so on, symbolically it's a 0, but numerically it doesn't turn out to be exactly a 0. So you have to interpret this a bit. So when you see a number like 10 to the minus 15, you should know that that's approximately for your language, and you should find this out before doing anything in the language or on your calculator. Figure out what approximately 0 means. So what's the numerical limit on that language or that calculator? So I know in terms of Python, it's around that 10 to the minus 15. So when I see this, even though these are values that are painted all over the screen here, actually I know this is approximately 0. So it's trying to tell me that these are all 0. So like we expected, L equals 0 there. And then here we see the angle bouncing around a lot. And that's because, of course, pi is just increasing without bound. So it's going 0 to pi, then and as it goes beyond pi, I actually added in some code that brings it so we know that an angle of 2 pi is the same as 0, is the same as 4 pi, and so on. So it reaches the pi, and then it switches over to, and I'm pointing with my finger there, I should point it. It's reaching the pi and then switching over to minus pi, and then after that it just keeps switching between the two. So the angle is just doing that. So yes, this is what we expect to see, and so this function is behaving or is being represented in the right way on these figures. Okay, any questions or comments so far?
So this session's been really helpful with regards to these plots. I was just wondering if we could maybe also then do a revision session on tutorial 4's plots again, because I feel like we went very in depth with these plots, but not as in depth with tutorial 4's plots.
Well, I was going to stop there on this one, so we can maybe look at the difficult parts of that, and we can also set up another Zoom session if you like. So let's just open that. Did we do that on Python or something else? I can't even remember. So tutorial 4, that was on the root locus diagrams, right?
Yeah.
Okay, so so just to close off on tutorial 5, so you have these you have these ways of developing your plots, and in the questions, it asks us to work through all these processes, right? And so we've just talked about this one, and here you can see it's more of the same polynomial style fitting. I would say the center point of all this is the Bode diagram. So of course the Nyquist, we must be able to look at these and figure out how to draw the Nyquist plots. But the Bode diagram is where we can really do that accurately. So make sure that you are able to do Bode diagrams well. And then the Nichols chart, of course, just comes from taking cross sections through the Bode diagram. So in question 2, it asks us for finding suitable values of Kp that control the processes. And of course, if we introduce a proportional controller, that has the influence of just multiplying the whole factor by Kp. So in that same code, you can play around with multiplying a factor, like if you just change this to a 5 or something. What does that do in relation to your functions? And then this question 3 asks for finding all these parameters for controlling the process. And also in tutorial 4, the same questions apply, right? Find the controllers that control those processes. And those are there not exactly for you to actually attempt, right? So I'll sort of admit that now. I wanted you to just appreciate how inconvenient it was going to be to find those controller parameters for all these processes. So in tutorial 4, we had all those, which one is this? Yeah. So in tutorial 4, we had outlined all these processes. Here's the list. And we talked about when we vary Kp, how that process responds. And we did that basically by creating a series of values for Kp and then redrawing the plot. And then, of course, if you wanted to do that for integral and derivative controllers as well, then that would be, let's say it was a pi controller. Then you'd have to worry about Kp and tau I. So then you'd have a two parameter space to search. And then for tau d, similarly, you would add another dimension, then that's a 3D space to search. So even though I listed it as a tutorial question, the intention here was for you to look at this and think, this is going to be so much more, so it's going to be so tedious to search for all these solutions now. And sort of the dramatic buildup is that, well, now we have the Nichols chart, and actually we can just shift the curve around, so by playing around with these parameters. So that's the reason we are building up to this this Nichols chart. It gives us a very easy way to find those parameters. And you are starting to see the implication of this when we talk about the Bode diagrams and how they how we can just add things together. So remember, when we add, let's say, an integral controller, then that's going to change our function by adding a different term to it. So let's say, yeah. So let's say f1 was this function. Then your controller, so def controller, that is actually going to add an s function. So that's going to give us, let's say, for instance, that's going to be a tau I times a 1 plus s. So it's doing nothing but add another term like the ones we already know how to deal with. So that's how we implement control. We recognize the type of controller or what type of functions it adds to our system. And then we just treat it as a new transfer function, and we Bode plot it, and we look on this figure for its closeness to the critical point. So that's where we are going with all this. So